Okay, so Unit 3 Physics. And as was just stated, physics is math. Nothing could be further from the truth. Okay? Math is a tool we use in physics, yes, but physics is not math. Okay? Let me tell you why. Physics is about understanding why things happen. Math is about calculating the numbers involved. Okay? So, do we use math in physics? Yes. Is it really hard math? Absolutely not. Okay? Guys, I got through university physics with only the 3 rules of algebra I taught you in chemistry. Okay? I am not a particularly strong mathematician. Okay? Last year my son was in grade 10. He was doing math 10C just like you guys are, and I struggled to help him. Okay? Like, I could figure out how to do it after like 2 hours on a question, and then I couldn't tell him what I did. Okay? I'm not terribly strong at math. It's never been my thing. But physics, no problem. Okay? Because physics isn't always about math. Okay? Yes, to solve for certain values, you're going to have to use some basic algebra. Okay? And in Physics 20, some basic trigonometry. Right? But really nothing more than you learned in junior high math. Okay? Solving for x and using sine, cos, and tan. Okay? In high school physics, that is the extent of the math that you will need to use in physics. Okay? So if you're really worried about all the math in physics, okay, you can take that off your plate. It's just algebra. Okay? Being able to manipulate an equation to solve for one part of it is the extent of the math you'll have to do. Okay? I've been teaching physics for, I hate to admit this, 25 years. Okay? Some of my best physics students are a lot like me. They're not terribly good at math. And vice versa. Some of the people who struggled the most with physics were some of the best math students. Okay? And I find that that tends to be a trend. People who are really good at math just want to do the math. They're like, there, just tell me the math. Like, well, no, you have to see what's happening. You have to be able to understand the relationships and the things going on here so you can get to the math. Their stumbling block was they couldn't get to the math. Okay? It's better to be able to visualize something and struggle to solve than it is to not even get to the solving part. Okay? So basically my message here is don't fear the mathematical component that is involved in physics because it's not as involved as you think. There's no calculus or anything like that. Okay? There's just basic algebra. In Science 10, that's it. It's just basic algebra. Right? Like, the most difficult formula you'll have to manipulate is probably this one. Okay? You'd have to solve for any one of those. All right? I mean, in Physics 20, yeah, it gets a little bit more involved. In Science 10, we do have some formulas where we combine formulas, but in the end, it's just being able to follow the rules of algebra. If I want to move something, I do the opposite. What I do to one side, I do to the other, and I move what's not attached to what I'm looking for first. Those 3 rules got me through university physics. I don't mean to brag, but I got 100% in physics twice in university. Okay? You don't have to be good at math to be good at physics. Okay? The two are not mutually exclusive. That's not the right term. They don't go together. Okay. Does that make you feel a little bit better? You don't have to be super at math to be really, really good at physics. Okay? All right, so what we're going to look at today actually involves no math at all. Okay? What we're going to look at today is energy. Because without it, nothing happens. Okay? It is kind of the basis of all physics. Okay? The strictest definition of energy is this. Energy is the ability to do work. Okay? At a very basic level, that's what energy is. It is the ability to do work. Okay? Energy comes in lots of different types. Okay? We're going to look at a lot of those types today. We're going to look at the history of energy because we've started every single unit with a history lesson. Okay, so now we have to start with the history of the basic part of physics, okay, which is energy. Okay? Now, here's the problem with energy. It's not a material. You can't hold it in your hand. You can make it, okay? You can transform it. You can transfer it to other things, okay? But it is not matter, right? Something that has lots of energy and something that has very little energy, they have the same mass. They're identical objects, okay? Like if I have a light bulb that's on and a light bulb that's off, okay? That one has more energy, but it's gonna have the same mass. It's not a material, okay? Which made it very difficult for people to quantify, measure, and explain. Okay? It's not like water. Oh, I can hold water in my hand. Here's water. It's wet. Okay? And it does stuff. See? You can dissolve things in it. You can't do that with energy. Okay? It isn't something you can hold in your hand. Okay? So, we're going to talk a little bit about the different types of energy today. Now, simple example here. Okay? I don't know if anyone has seen this ever done. Okay? It's done more ceremonially now than it used to be. Okay? It's called the Inuit blanket toss. Okay? The Inuit blanket toss actually was a hunting tool, okay, that the Inuit used to sneak up on herds of like caribou and things like that. Because where the Inuit live, in the tundra, it's very flat. There's no trees. There's no tree you can climb that will let you see further over the horizon. Makes it very difficult to sneak up on your prey because there's no cover, okay? No high points to look down from. So what they would do is they'd take the smallest person in the group, put them in the middle of a blanket, and have everybody else grab the blanket, throw them up in the air as far as they could. And then that person would be able to see over the horizon just a little bit, okay? And then they could kind of encircle the herd of caribou that they would find. Okay? So it was a useful tool. Now, in order to throw somebody up in the air, are you going to use many different types of energy?
Yeah.
Yeah, actually you are. It seems at the very basic level like it's just throwing someone up in the air. But where does the energy to throw them come from? Who's throwing them?
People around them.
The people around them. Okay, so the people around them are like contracting their muscles, right? Exerting force through their muscles. Where do they get the energy to do that from?
Muscles.
What's in their muscles?
Food or sugar.
Yeah, sugar, which came from their food. Okay? So there's actually a lot of different conversions of energy that result in that person having gravitational potential energy as a result of being way up in the air. Okay? And it starts out with chemical energy in the human body. Okay? Sugar. Right? Our mitochondria turning that into ATP, okay? Energy that is used to contract the muscles. So we're turning chemical energy into mechanical energy. That's movement. Okay? That mechanical energy is used to do work by exerting force on the blanket. The blanket then pushes on the person, increasing their mechanical energy, kinetic mostly, okay? By throwing them, making them go faster. Okay? And then once they leave the blanket, their kinetic energy converts into gravitational potential energy. As they go higher and higher, they also go slower and slower. Okay, so kinetic energy turns into gravitational potential energy. They're at their maximum height, they look around, and then gravity pulls them back to Earth, converting their gravitational potential energy back into kinetic energy. And then the people holding the blanket had better be ready, because now they need to hold that blanket tight and allow the energy they gave that person to do work on them while they absorb the energy of that person. Okay? There's a lot of energy conversions that go on in something as simple as throwing something up in the air. Okay? That's what we have to be able to do in physics, is look at a situation and see it from that point of view. That's something that some people struggle with. Okay? It can be hard to see into the inner workings of things sometimes. Okay? So soon, if you become good at physics, you will see the world like I do. At first, it's scary. Okay? But then it allows you to understand how the world works a little bit better. Not the like social world. I don't even try to understand that. Okay, just the physical. Okay. All right. Oh, are we going to be like that today? Okay, So as I was talking about earlier, the idea of energy, okay, was difficult for scientists to explain, okay, for a very long time because it wasn't something that they could hold or like measure or something like that, right? So the sun's energy causes snow to melt in the spring, obviously, okay? It comes from the sun as radiation, okay? In all different wavelengths, visible light, infrared, X-rays, gamma rays. Thankfully, those two get filtered out, okay, before they get to the ground. Okay, but the stuff that does get to the ground, okay, the infrared, the heat, okay, can be converted into latent heat, okay, which melts the ice, turns it into water. Okay, so the idea of this concept went hand in hand with our ability to harness it. Okay, we actually were better able to use energy than to explain it. Actually, that's kind of the technological history of the human race. Okay? Hey, I can do this thing. Doesn't matter that I don't really understand how it works. I was able to do it. Okay? We had kind of a lot of things that went that way. Okay? So energy is still difficult to describe because it's an abstract idea and not a material object. Okay? Now, most common form of energy that we use to power our society would be what? We use this to get electrical. Electrical, most often, at least in Alberta especially, comes from this.
Fossil fuels?
Yeah, fossil fuels, which are an example of chemical energy. Okay, especially in Alberta. Okay, we can tell ourselves that it's all the new solar farms and the wind farms in Pincher Creek, but the reality of it is those comprise a very small percentage of our total power grid. Most of our power grid comes from coal and natural gas being burned to turn a turbine. Okay. So chemical energy, okay, was really one of the earliest types of energy that humanity understood. Wood sets on fire, makes me warm. Okay, that was early man, right? We used chemical energy, it kept us warm, it was able to cook our food, which made us healthier because we weren't eating meat that maybe wasn't cooked enough. Okay, so it was an important thing. Now, not all substances obviously yield the same amount of energy. This is something that Antoine Lavoisier studied. You're not going to need to know his name. Okay? But what he studied was the energy released by different amounts of fuel. He did what's called calorimetry. He took a specified amount of water and a specified amount of mass of each fuel. So let's say 100 grams of wood, 100 grams of coal, 100 grams of oil. Okay? And he just recorded the temperature change for the water that he had. Okay? Obviously, the more energetic fuels would heat the water more. Okay? It was an important discovery because we want to use the most efficient, or highest yielding energy fuels. Okay? And that's been the pursuit of humanity for a very long time, finding the best, highest energy fuel. Okay? The first automobiles didn't run on gasoline. Okay? They ran on like oils and things like that. That wasn't nearly as efficient. Okay? We've refined our process and made that fuel more energy yielding and cleaner. Okay? More importantly. Okay, so when wood burns, the energy in the cellulose molecules is released. And this is true for any fuel. Okay? If we look at something simple, like propane. So propane has 3 carbon atoms and 8 hydrogen atoms. The molecule looks kind of like this. Okay, so that's a propane molecule. Energy is stored in the chemical bonds between the atoms. So anywhere where you see a line, okay, it represents a chemical bond. Energy is stored there. If I break those bonds, the energy in those bonds is then released, okay, as heat. Okay, so when I burn propane in the presence of oxygen, those break and I end up with carbon dioxide and water, okay, which are lower in total energy than propane was. Okay, so I'm releasing that energy by breaking those bonds. That is true for any chemical energy release that involves combustion. Okay? Now, are there other forms of chemical energy? Yeah, you use it in your batteries. And the battery that powers your cell phone, okay, that lithium battery, okay, that's a chemical reaction. Right? It yields energy. The nice part about it is it's reversible. When you plug it in, you can make it go back the other way. Does that work forever? How many of you have had to replace the battery in your phone?
Not yet.
Really?
Just 30
just buy a new phone.
Usually.
Here's what's wrong with society, people. Okay, you're just throwing that battery in.
Most phone companies don't let you buy phones anymore. You pretty much rent it off them, and then you replace it with a new one every 4 years or whatever.
They try to do that. I keep a phone until it breaks.
That's my.
Like breaks. If the battery goes, I put a new battery in. It's not hard.
My
Okay.
dad does that.
Yeah, it's actually quite easy. Okay, you have to get the little toolkit. It costs like $4 on Amazon. Okay, and it's just like a special screwdriver and stuff. You can take it out, put a new battery
But you
in.
don't wanna get like a rip-off battery from Amazon.
No, definitely buy like the legit battery, or you're gonna have like the Samsung blow-up phone, okay, or Apple blow-up phone, because it's not Apple's problem or a Samsung problem, it's the battery you put in. Don't cheap out on the battery, okay? But yeah, you can replace it. But either way, that lithium-ion battery goes in the garbage, okay? Or it goes to hopefully to the recycle place where they do whatever they do with it, okay? But it's certainly chemical energy, okay? It's a chemical reaction that powers your phone, turns into electricity directly, okay? And of course, some heat. You've probably noticed sometimes that your phone gets warm when you're using it, okay? All right, so chemical energy is just energy that's in the bonds of a chemical. When those bonds are broken, then the energy gets released. If it's something that's rechargeable, you can put energy back in, reform those bonds, and essentially reverse the reaction, okay? You can't unburn a fire though, okay? That is not a reversible reaction. Okay, now, so that's chemical energy. Now, what we're looking at here is the other kinds of energy, the one we usually get from chemical energy. Okay, chemical energy gives us either heat, electricity, or mechanical energy. Okay, if it's mechanical energy, that mechanical energy usually comes first from heat. So it's like chemical, heat, and then mechanical, like your car, for example. Okay, in your car, when you burn fuel, okay, the engine makes a lot of heat. Okay, that heat causes gases to expand, which is what pushes the piston down in your engine. Okay, it's the explosion of the gasoline. Okay, the expanding gases push the piston down. Okay, so we have chemical energy to heat to mechanical energy. Okay, it's actually incredibly inefficient, but it's cheap and easy, which is why we do it. Okay. If we're talking about a battery, okay, a battery is converting electricity directly to mechanical energy. If you have, let's say, a hybrid car or an electric car, okay, it's going to convert it directly to electrical energy. That is more efficient. Okay, does anyone have an electric car at home? Okay, I have one that's plug-in hybrid at home. Okay, and I can tell you that it is definitely more efficient to run on electricity. Okay, if I have it running on combustion only, okay, it costs me about, let's say, 7 liters per 100 kilometers, 7 times $1.50, let's say about $12, okay, to go 100 kilometers if I'm on just combustion. Okay, if I have it plugged in and I run it on just electric, it costs me about $2 to go 100 kilometers. Okay? And yeah, I mean, part of that is the price of electricity is cheaper than the price of fuel, but it's also more efficient. Okay? I'm not wasting a bunch of energy as heat when I'm using electricity to move the car versus combustion to move the car. Okay? Your internal combustion engine in your car uses about 30% of its energy to cool itself, to run the radiator and the water pump, okay, so that the car doesn't die. Okay, it actually uses 30% of its energy just to do that. Okay? So it's not terribly efficient. We're getting better. Obviously, we make more efficient cars all the time. Okay, but chemical energy is not as efficient as other forms. Okay, now if we're talking about electrical energy is the work done by moving charges. Okay, so when you hook up a battery to something, electrons move through the wire. Okay, charges go through the wire. Whatever the wire is connected to, okay, those really fast-moving electrons power it. Okay, whether that's converting it to light, okay, or whether that's converting it to mechanical energy, the idea is the same. The electrons get to that device and they slow down. And when they slow down, they give their energy to that device. Okay, so if it's a light bulb, okay, like an old style tungsten filament, Thomas Edison style light bulb, okay, those electrons hit the tungsten filament, there's a lot of resistance there. Tungsten does not conduct electricity well at all. So the electrons slow right down, and that generates heat. okay? And the filament glows white hot, okay? Gives off a lot of light, but it also gives off a lot of heat, okay? And then those electrons go back through the wire, but they're moving much slower. Okay, if we're talking about an electric car, okay, or an electric motor, like in a fan, for example, okay, the electrons come in, they hit the electric motor, okay, they cause the magnets to switch their polarity, okay, and that causes them to slow down, but it does mechanical work. Okay, it's much more efficient because it doesn't generate as much heat. Okay. All right, this thing here, this picture, that is the Volta pile. That is the great, 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 great granddaddy of the battery. Okay. It is simply a bunch of metal discs with moistened paper in between, okay? And the metal discs, I can't remember what metal they were made out of, but okay, they, because there was moistened paper in between, there was a potential difference in charge between the top and bottom of the battery. That was more charge at one end than the other, which would result in the charges wanting to go from one end to another if they were connected. Okay, which is exactly what we do with batteries today. One side of the battery has a high potential, the other has a low potential, and the electrons want to flow from high to low. Okay, so out the negative end and to the positive end. Okay, everyone follow me there? Okay, now, with a modern battery, okay, they go out the negative end and into the positive end. Okay, but eventually, that battery dies. Why?
Because it becomes equal on both ends.
Yeah, the potential difference is lost over time. As you use the energy in it, the potential difference between top and bottom is lost, okay? But that also means that the battery changes a little bit. Some of those electrons don't make it all the way back, right? So the potential in between the top and the bottom changes. Anyone ever do the battery drop test to see if it's live or dead? Okay? The reason that that works is because of exactly that, okay? When a battery is live, you can drop it and it will stand. If it's dead, when you drop it, it'll fall over because there's more mass at the bottom when it's live. I think that's the way it goes. I might have that backwards. Okay, but if you take like a AA battery and you just hold it about this far off the table and drop it and it stands up, okay, so drop it vertically, it stands up, it's still good. If you drop it and it tips over, it's dead. Okay, it's not the most reliable way, but it can tell you if one's live or dead generally. All right, so the Volta pile is the first battery. It converted chemical energy to electrical energy, okay? Moving charges, okay, that could then be used to do something else. Okay, so I would say you should probably know Volta and his pile, okay, because it's about electrical energy. Okay? He's kind of an important guy. You know you're important when your name sounds like a unit of measurement for something in physics. Volts. Yeah, exactly. Okay. It's like newtons. They're the units for force. Okay? Joules, the units for energy. Okay? All that kind of stuff.
Celsius.
Mm-hmm. Okay, now, once electricity was, the idea that moving charges could be used to do things, it was also discovered that moving charges had a lot of other effects, okay? And that there was a very close relationship between electricity, moving charges, and magnetism, okay? Moving charges create magnetic fields and electrical fields, okay? And these fields have areas where they can influence things, okay? That is where they can do work and exert a force, okay? So Ørsted, okay, discovered that electricity can produce magnetic effects, probably by accident, but here's what happened. Okay? He had a current-carrying wire and a compass. Okay? He placed the compass on the table, and of course the compass pointed north, as compasses do. Okay? And then he turned on the electricity that was going through the wire. And the compass went from pointing north to pointing along the wire. Now what do compasses respond to?
Electromagnetic fields.
Yeah, magnetic fields, but in this case it was an electromagnetic field, yes. Okay, so they respond to magnetic fields. Most of the time, it's the Earth's magnetic field, which is why they point north. But they can also respond to localized magnetic fields. If you ever just take a small magnet, put it next to a compass, you can make the compass do whatever you want, okay? Because once you put that very, very small magnetic field very close to it, it becomes more powerful, okay, than the Earth's magnetic field because it's closer. Okay? Even though it's like way smaller, it's just closer. Okay, everyone kind of follow me on that? All right, so all field forces work that way. The closer to the source you are, the more intense the field is. Okay, it's the whole idea behind, like, you know, we had this thing happen years ago where they wanted to put a cell phone tower out here, which would have been awesome because the cell reception here is terrible.
Yeah.
Okay, because we're out of the line of sight of the one down in the middle of town. Okay, so they were going to put one here, and there was a group of people who resisted it and actually got it axed. Okay, because of no, the magnetic field will cause brain tumors.
Are you kidding me?
I am not kidding you. It is not the smartest voice that gets things done, it is the loudest voice that gets things done. I'm sorry, guys, there's a sad life lesson for you. Okay, but I remember the principal coming to me and Mr. Dickey and going, I've got these people telling me they don't want the cell tower here because it's gonna cause brain tumors. This is a magnetic field thing, and we both like face palmed ourselves a concussion. Okay, we're like, are you kidding me? And we showed her the map. It's super easy. Okay, it's like any field force is some constant multiplied by, okay, for magnetic field, it's like electrical over R squared. Okay, R is the distance you are from the source of the magnetic field. The further away you get, there's exponentially less effect. So unless you sat on top of the cell tower, okay, all day, every day, the strength of the field decreases exponentially. So if I'm 1 meter away, the field is very intense. If I move 2 meters away, it's 4 times less intense. If I move 3 meters away, it's 9 times less intense. 4 meters away, 16 times less intense. And since you're probably not 16 meters from that cell tower at any point, okay, you can imagine how intense the magnetic field gets as you move further away, okay? We're like, if that was true, every compass in town would point to the cell tower. Do they? Maybe if you stood right next to the cell tower, your compass might do this, okay? But it's not, okay? It's just not that intense, but you know, loud doesn't always equal right or smart. Okay. So, that's, by the way, gee whiz. That was so dumb. GE. Okay. So, what Oersted discovered is that, yes, an electrical current can cause a magnetic effect. And you can feel this sometimes. If you walk, like if you see those high voltage wires, okay, if you go underneath those, your cell phone doesn't work as well. Okay? There is a magnetic field around those current carrying wires that can, you know, affect your cell phone reception. Okay? If you had a compass, it would probably affect the compass a little bit if you were right underneath them. Okay? But most of the time we don't run power, like big high voltage lines over people's houses. Okay? And for exactly that reason. They would be really close and there would be effects like that. Okay? But not nearly as bad as talking into your cell phone all the time. Okay? Holding your cell phone next to your head puts a magnetic field very close to your head all the time. And it generally doesn't cause brain tumors. Yeah? Okay, so just think about it. It's really like pseudoscience.
Imagine those people calling up the people
Yeah.
and trying to make the cell tower.
Exactly. It's just ridiculous. Okay, so electrical fields or electrical currents can cause magnetic effects and vice versa. A magnet can cause electrical currents. Okay, so these two things were discovered by two separate people. Oersted discovered that electricity has magnetic effects. Faraday discovered that magnets can produce electric effects. Okay, how many people have heard of a Faraday cage? Okay, so a Faraday cage is like, it's basically just a metal cage, okay? And if you stand in it, you are essentially immune to like all the electricity in the area, okay? And it can even shield against like cell phone reception and things like that.
We have a cabin. We have a screened-in like eating area, and my dad keeps calling it the Faraday cage because we couldn't get like Wi-Fi in there. Even though our house is right next to it,
Mhm.
you can't get Wi-Fi, and it's poor cell service in there until they put like an extra router.
Yep.
So we called it the Faraday.
The Faraday cage, essentially how it works. Okay, yeah, but it's a true thing. But what Faraday discovered is that if he had a coil of wire and he pushed a magnet through it, he could generate an electrical current because the magnet would repel the electrons. It would push the electrons through the wire, okay, and make them move. moving current, moving electrons are an electrical current, okay? So this is actually how some of the first generators were built, okay? They would have basically some sort of motor that would move a magnet up and down inside a coil of wire, okay? If the magnet's moving up and down through the coil of wire, it's producing alternating current, up and down, AC. Okay?
Think of the washroom.
Okay. Okay, so if you hold a magnet above iron filings, obviously the filings move towards the magnet, so magnetism is a form of energy. Okay, Oersted did this current carrying thing, okay, and Faraday did the, showed that the reverse can happen. And then people thought, okay, so we know we can get electricity, in these ways. Can we make heat into electricity? Because heat's easy. We can make heat all the time. Okay? And there actually is a way to do that. Okay? You can turn thermal energy directly into electricity. It's incredibly inefficient, but you can do it. Okay? So Seebeck, okay, Thomas Seebeck showed that that could happen. Basically what he did is he took two different metals that had different abilities to conduct heat. Okay? And he started heating them. And he found that as the heat traveled through one and the other, because it traveled faster through one than the other, it created moving electrons, okay, which caused the compass needle to turn from pointing north to pointing along the bar, okay, indicating that there was an electrical current being made in that bar. Okay? We actually use this technology all the time. Okay? It's another thing that we put inside of electric and hybrid vehicles. Okay? Anyone have a hybrid vehicle? Okay, so in a hybrid vehicle, the brakes work differently than they do in a combustion engine. Inside the brakes is what we call a thermocouple. A thermocouple turns heat directly into electricity. When you apply the brakes, do they get hot? This is a way, it's called regenerative braking. We actually use the mechanical energy of the car, convert it into heat, and then let the thermocouples charge the battery with it. It's a way for us to get some of our energy back. If we don't have that in our brakes, the energy just bleeds away to the environment and it's wasted. Okay? But this is a way to recover some of it, which is why it's called regenerative braking. Okay? We allow the heat generated by our brakes to be turned, some of it, not a lot, but some of it, into electricity that goes back and charges the hybrid battery.
It's so weird though when you drive cars that have regenerative braking because you let go of the accelerator and it'll just stop.
Yeah, it starts braking right away. It
And
uses
you
that.
don't roll
Yeah.
forward where you usually do on a combustion engine.
It does require you to get used to it working a bit differently. Okay? Our car actually has a thing called a brake coach on the dash. Okay? And it tells me how much of my braking energy I got back. Okay? Now, it says 100% if I do a good job, but it's not actually 100%. It just means I got the most I could have possibly gotten, which means I didn't pile on the brakes and come to an abrupt stop, because I did that and I got like 5%. Okay? But if I start braking a long way back from the light and I brake slowly and efficiently, I get 100%. It's become a game. Every
I do
time
that
I do
anyways.
it, every time I do it, I'm like, hey Reed, look! 100%, I got 100% again. And he's getting kind of tired of it. It was fun like the first few times, but that's never ceased to be fun for me. Okay. So it gets your energy back. You get some regenerative braking out of that, okay? And just uses a thermocouple. It uses what Seebeck discovered hundreds of years ago, okay, that we can use, okay? We also use this in circuit breakers. Right? How many people have ever blown the breaker at home? Plug too many things in, right? Usually the hair dryer is the thing that pops it at our house, okay?
Jam the fork in the socket.
Okay, well, they'll do it too. It'll also blow other things, like the person holding on to the fork.
Yeah.
Yeah.
Playing the coffee machine and the water boiler.
Yeah.
Kettle?
High draw
Yeah.
kettle, yeah, high draw, usually things that are converting electricity to heat are the things that are gonna pop it. So what happens is, as you've got the electricity going through that circuit, the wires start to get hot. Okay, this caused house fires like crazy before fuses and circuit breakers were a thing. Okay, so basically it prevents you from starting an electrical fire that burns your house down. Okay, so if you get too much current being drawn through a wire and the wire starts to get hot, inside your circuit breaker is a small thermocouple. Okay, if that thermocouple starts to make enough electricity to pop the circuit open, which now allows no electricity to go through the circuit, and the circuit cools down. Okay? If you've ever just gone downstairs and tried to flip that breaker back right away, sometimes it pops again. Okay? And you have to wait like a good 5-10 minutes for the circuit to cool before you can get the breaker to stay closed. Okay, it's all a safety thing, it's designed to prevent fires in the house. Okay,
I saw it happen in a cartoon where the other guy put a fork in the socket and I didn't think it was real.
oh, so you decided to try it?
Yeah.
They did it on Seinfeld once too.
It hurt.
Yeah, they stuck a paper clip in the circuit breaker, or in the outlet, and it popped the circuit, and then, I can't remember why they were doing that, but it shut off the auto feeder for the cat in the apartment, and then they were having to feed the cat by putting thinly sliced deli meat under the door. Why did I can't- I'll have to watch that. Okay, so does that make sense? So Seebeck made the first thermocouple, so we can convert heat directly to electricity as well. All right, now, so the difference in temperature in that thing that he made in the thermocouple, okay, caused the electrons in the metal to move. That's what produced the electric current. Okay, and then obviously for Thomas Edison, he did the opposite. Okay, so Seebeck discovered heat could turn into electricity. Okay, but Edison discovered electricity could turn into heat. That's how he invented the light bulb. Okay, so basically what he did is he found that metals that are poor conductors get hot when you try to run electricity through them. And he found that tungsten in particular would glow very, very brightly, white hot, when electricity flowed through it. Now, what was his challenge in inventing the light bulb? Because he's actually well known for saying, he was asked, did you ever feel like a failure? You tried like 1,000 times to build a light bulb before you got it right. And he said, nope, I discovered 999 ways how not to build a light bulb. He's totally a glass half full person.
The challenge, I think, is making sure the tungsten doesn't burn.
Yeah, exactly. Okay, the tungsten would burn. As soon as it got hot enough to glow and make light, it would burn up. Okay, so the purpose of the glass part of the bulb is actually to be a vacuum. So there's no oxygen inside, so that the tungsten can't burn. If there's no oxygen, there's no combustion. Okay, so the tungsten would just get really, really, really hot and glow, but it wouldn't burn.
Actually,
Okay.
I put argon in it too.
Yeah, he had a noble gas of some kind, I think, in there as well, but like it's basically just that there was no oxygen, it was an oxygen-free environment. When bulbs, when they burn out, is usually when there's some flaw, enough expansion and contractions happen in the gas, in the glass, sorry, and some oxygen gets in there and then they burn out. Okay? All right, now, nuclear and solar energy. So, where do we get nuclear energy from?
Nuclear power plants.
Okay, where did they get it from? How do they make it? Splitting atoms, right? They use the energy that normally holds an atom together as energy. If they can make that atom break, the energy that's holding it together will get released. Okay, the bigger the atom, the more energy there is to be released. Okay, so nuclear energy is the potential energy that's stored in the nucleus of an atom. Okay, when the nucleus of an atom is split, it gets released, or when you push two nuclei together and make a new atom, energy is released. Okay, that's fusion. Now, for a very, very long time, people looked up at the sun and they went, oh God, that's bright. That's terrible. But they figured, because it was warm, that it was a big fire. Okay, and they were right. But it wasn't the kind of fire they thought, because fire that they were associated with, like wood and coal and things like that. Okay, that's not the kind of fire that the sun is, because what is there none of in space? Yeah, no oxygen. You can't have combustion in space, it wouldn't work. Okay, the sun is a nuclear fire, a really, really big one. Okay, and it's a nuclear fusion fire. So what's happening in the sun is, because the sun has so much mass, it creates a ton of gravity. The more mass something has, the bigger its gravitational field. Same thing as I showed you with the magnetic field. All field forces are the same. Okay? So the sun's mass is huge, and it's so huge that it creates enough gravity that it forces hydrogen atoms together into helium atoms. That's nuclear fusion. Okay? And it does that countless times in a second. So it releases huge amounts of nuclear energy in the form of radiation that travel outwards. Okay? People didn't understand that at the time, so that's why they're like, oh, it's just a big fire in space. Well, if that was the case, the sun would have burned out after like 5,000 years, if it was like a combustion fire. Okay? But luckily for us, it's been burning for about 4.7 billion years, and it's probably got another 4 billion in it or so. So certainly we can file the sun burning out under not our problem. Okay, that's certainly not something we're gonna have to worry about. Okay, so it results from this nuclear hydrogen nuclear fusion, okay, reaction. Okay, so only about 5,000 years if it was a actual fuel fire would have lasted. Okay, so nuclear and solar energy, same thing. Okay, they come from nuclear fusion. Okay, nuclear energy is any energy stored in the nucleus of an atom. So it is a type of potential energy, as is chemical energy. Okay, chemical energy is potential energy as well. We don't get heat until we release it and turn it into something else. All right, the energy we're going to be most concerned with is mechanical. That would be potential and kinetic. Okay, so motion energy or mechanical energy. That's what we study most in high school physics.
Electricity.
What's that?
Don't know anything on electricity.
No, they actually took it out of the physics curriculum 15, 16 years ago.
We did it last year in grade 9.
Yeah, you do it in grade 9. They actually moved it down to grade 9.
So that's the last time we learned about electricity.
You'll learn about electrical fields and things like that, but not like currents and circuits and stuff like that. Like you learned about parallel and series and all of that in grade 9. We don't do it again in high school. Yeah. Okay, so Newton's cradle. Okay. How many people have seen that thing before? Okay. Would you believe that that got Newton in a lot of hot water?
Yeah.
People thought he was a witch. That was a different time, okay? But he picked up the ball on one side and let it go, and when it hit the other balls, the ball on the far side went up. And you can imagine in a more primitive time that people would be, oh, how did you do that? You're a witch! And to which Newton would go, no, you tried. Hell no, I'm not a witch. You're not going to get me in trouble.
I'm not trying to get burned to
That's right. I don't want to get weights tied to me and thrown in the lake or burned at the stake. No. You're the witch here, not me. But he had to very quickly kind of try to explain what was happening. And his explanation, was about, I don't want to get burned alive. So, well, no, there's this living force. Oh, witches have living forces. What do I do now? But it was basically this idea that by pulling one ball away, he was trying to explain energy. But again, it wasn't something anyone, including Newton at the time, really understood. He said, I give it something, and when I let it go, it takes that and it transfers it to the other balls. Okay? And it goes through them to the one on the far side. Since there's nothing on the far side to stop the last ball, it gains the force that I gave it, this living force that I gave it, and it makes it move up on the other side. Okay? And eventually, a Newton's cradle stops. Okay? Because the energy that you initially give the ball, okay, sure, each time it swings, it gets transferred through, but each time it swings, you also hear sound. You hear the click, click, click each time. Is sound a form of energy? Okay, where does the energy for that sound come from? The energy you gave it. That's why it doesn't go on forever. Okay, there's always a little bit of energy lost each time the ball hits another ball. Okay, does that sort of make sense? Okay, so it was a great example of how energy could be converted and transferred to and from objects. Okay, it just you had to have someone with an open enough mind to listen and not go which. Okay, in order to kind of get that understood. So later after that, German philosopher Gottfried Leibniz reasoned whatever caused the ball to move resembled a force that could be transmitted through them, living force, or vis viva, which later became energy. Okay, and from there he discerned that energy came in two different types that could be combined together. Okay, those two different types are kinetic. That's the energy due to motion or movement. And potential. That's what you give it initially. You pick it up again and move it against gravity. So gravitational potential energy. When you let it go, gravity pulls it down, turns that gravitational potential energy into kinetic. It hits the other ball, it transfers through, okay? And a ball on the far side gains that kinetic energy and moves upwards. So we should know then these terms here. Okay? Kinetic energy has to do with motion. Okay? Gravitational potential energy has to do with position. And it's possible for something to have both, in which case it would have mechanical energy. Okay, so thinking that way, what position would result in an object having no potential energy?
On the ground or like a flat area?
Right, on the ground. Because then it can't fall. It has no potential to fall. Okay? Something can only have gravitational potential energy if there's the potential for gravity to pull it downwards. This desk has no energy at all, really. Okay? It has no potential energy because it's already on the floor. And it has no kinetic energy because it's not moving. Now, if I pick it up and throw it, which I wouldn't do, okay, then it would have both. Okay? It would be above the ground and moving, and then it would have mechanical energy because it would have some kinetic and some potential. Okay? All right, everybody good with that? Okay, we're going to take a 5-minute break here, and then I'm going to talk about the next thing. Okay, so mechanical energy, like I said, is going to be one of the things we deal with a lot in physics, okay, because it has to do with movement and position, and that's the kind of thing that we look at in high school physics, okay? But thermodynamics are also important, okay? Thermodynamics, as the name would imply, has to do with heat and movement, okay? Dynamic means to change or move, thermal means heat, okay? So thermodynamics is how heat or thermal energy moves from one system or object to another, okay? Now, how many people have had their parents, you open up the door and you're talking to somebody outside the house and it's really cold outside, and they say, you're letting all the cold in. You can't let cold in. You can let heat out, okay? Energy always flows from high to low. That's how nature works. Doesn't matter what we're dealing with, it flows from high to low. Okay? So you're actually letting all the heat out. Okay? You're not trying to heat the whole neighborhood. Yeah, okay, those things, those are true. Okay? Because they involve energy flowing from high to low. Okay? You cannot transfer coldness. Okay? That is not possible. You can take energy away from something to make it colder. Okay? But you cannot transfer coldness to something. That is a lack of energy. You are cold because you lack energy. I can't transfer a lack of something to you. Okay? I can take away what you have. That would make you colder. Okay? But I can't give you colder. Okay? That sort of makes sense? Okay? Now this was discovered, okay, early on, but it was Joseph Black, okay, who was a Scottish physicist, who kind of quantified it for everybody by doing an incredibly groundbreaking experiment. He put a cold object in a cup of hot water, and he discovered that the object got warmer. Shocking. Okay? But it definitely said that something went from the hot water to the cold object. Okay. Now, on the same token, the hot water got colder, okay? But it still remained warmer than the cold object. And if left to their own devices, eventually the temperatures would become equal. Okay? Now, that led him to believe, okay, that heat was this invisible fluid, okay, that flowed from there was a lot of this early on in the science of energy, these invisible fluids and things like that, because again, energy is not something you can hold in your hand, but it does these things that make it seem like it should be. It flows from one thing to another, like a fluid would. Okay? Just like water flows downhill from high altitude to low altitude, and energy, heat, flows from hot to cold. Okay? So they called it this caloric fluid. okay, that would flow from hot objects to cold objects. The problem with that idea is that fluids have mass. They're a material, okay, which would mean that as an object got hotter, it should also get heavier, okay, which doesn't happen, okay? Getting hotter doesn't make you heavier, okay? It just makes you hotter. So this idea of these invisible fluids was okay for kind of explaining energy going from one place to another, but it didn't explain it like physically well in terms of this whole mass thing, okay? So this started the science of thermodynamics, okay? So Black was trying to perfect his caloric theory for thermal energy, heat, okay? Other scientists were applying it to atomic motion, okay? That atoms or the particles that are in a hot object are moving faster than objects in a particles in a cooler object, okay? And when you put them together, the movement of the particles in the hot object can be transferred by contact to the other object and make its particles move faster, which is of course what we know to be true now. Okay, everyone follow me there? Okay. All right, so here's the thing. Up until now, you have probably used the word heat to describe thermal energy. Okay? You'd say, oh, we got to put some heat in here. You know, or, oh, that fire is making a lot of heat. Well, that's actually not the proper use of the word heat. Okay? That fire is making a lot of thermal energy. Okay? We need to get some thermal energy in here if it's cold. Right? But in actual fact, the word heat is a transfer of thermal energy. Okay? So I feel heat because thermal energy is being transferred from a hot object, fire, to me. Okay? But heat is not energy. It's the transfer of thermal energy. Okay? So two definitions that are going to be important here. Heat is a transfer of thermal energy, and work. Work is a transfer of mechanical energy. So heat and work are alike in that they are both transfers of energy. They are what happen when there's a difference in energy between one thing and another thing. Okay? If that difference is thermal energy, one object is hotter than the other, heat will happen. Transfer of thermal energy. If one object is more energetic, that is moving faster than another object, it will do work on that object and transfer mechanical energy to it. Okay? Everyone all right with that? Does mechanical energy work the same as heat in that it has to go from the higher energy object to the lower energy object? Yes. Okay. If you're stopped at a stoplight and somebody's texting and driving and rear ends you, okay, did you transfer energy to them? No, you can't transfer what you don't have. You were stationary. You have no mechanical energy. They hit you. Okay? They now have less and you have more.
Well, technically you have mechanical energy because your camshaft's spinning, because your engine.
Your engine has mechanical energy, but the car, because it is stationary, doesn't.
Oh,
So it's possible for a system to have energy in one part.
that makes sense.
Yeah. Okay. Everyone okay with the idea of those two things? That comes up as a multiple choice question all the time. Okay? Heat and work are both transfers of energy. Now, because they're both transfers of energy, okay, we can talk about how you can turn thermal energy into mechanical energy and vice versa. Okay? It's much, much easier to turn mechanical energy into thermal energy. Why? Why is it easy to turn motion into thermal energy, but not as easy to go the other way?
Because when things move, they get hotter.
Exactly. Anything that's moving, any two surfaces going past each other, there's friction. Okay? And friction is a force that does work, where it takes energy away. It's always working against you. okay? And as a result, it's gonna turn mechanical energy into heat, okay? One of the biggest things for increasing efficiency is to reduce friction, okay? If you were to look at, let's say, motor oil 30 years ago versus now, okay? Part of the reason cars run more efficiently now than they used to is because we have better lubricants for the engines. We have synthetic oils that don't break down under high temperatures, and they remain viscous and they remain slippery, okay? Versus conventional oils that, you know, do break down and they become less slippery, okay, and increase wear and things like that, okay? Air resistance. Look at a car from 30 years ago versus a car today. Okay? Everything today looks like a teardrop. Okay? But 30 years ago, everything looked like a box.
And it looked way better.
Yeah.
But they were not nearly as aerodynamic. Well, air resistance is a type of friction. If you can make the air go over the car and slow down less as it goes over the car will be more efficient. Okay? Anything that reduces drag of any kind, okay, is going to be more efficient. Okay? Because drag is going to produce heat. It's why meteors burn up when they hit the atmosphere. Okay? It's why spacecraft have to have heat shields, okay, and come in at the right angle. If they don't, okay, going through the air results in so much drag that there's so much heat produced that they'll burn up. Okay? All right, so in 1800, Benjamin Thompson, who was an American, born as an American, later became Count Rumford. Don't ask me why that name change happened, but whatever. Okay? He became the Minister of War in Bavaria. The job as the Minister of War is to supervise the production of cannons. Okay? Because, well, that's what we had. To make a cannon, you take a big lump of iron and you bore it out. You drill out a cavity or a cylinder inside of it. Okay? And what you're going to do with that cylinder once it's bored out is you're going to pack gunpowder in it, and you're going to put a big ball in front of all of that, and then you're going to light that candle, okay? And then the gunpowder will explode, and the expanding gases will push the cannonball out of the cannon. Okay? It's not rocket science. Well, it sort of is, but it's not really. Okay? So all you do is you use these expanding gases. So you have chemical energy being converted into heat, which causes mechanical energy because it expands and is under pressure, okay? And that transfers mechanical energy to the cannonball and shoots it out of the cannon, okay? Here's what Thompson discovered, though, okay? He noticed that his workers could take coffee breaks, or tea breaks, okay, periodically, because they could boil water on the cannons they were boring out, okay? Because a bore is just a big drill operated by a bunch of people. Okay, so they're turning the drill and they're boring out this big lump of metal. Okay, has anyone ever used a drill before? You ever touched the bit after? It's hot, right?
Yeah.
Okay, well imagine that on a much bigger scale. Okay, so you got this big metal lump and you got this metal bit, okay, and you're turning this thing, okay, and you're boring away inside of this thing and you've got a tea kettle sitting on top of it. Okay, that stuff would get hot enough to boil the water. Okay, that's how the coffee break was invented, probably. Okay? So if you worked hard, you could get the water to boil, and then you could have a cup of tea. Okay? Now, you've got to be careful. Don't lean against the cannon during the coffee break. It's hot. Okay? Workplace safety is probably not a thing then. Okay? But it was a thing that happened. He found that this heat had to come from somewhere, and the only source of energy was the people. Okay? They were turning the bit. So we were taking chemical energy in the muscles of the people, turning it into mechanical, turning it into drag and friction, which turned into thermal energy, which then boiled the kettle. Okay? So he found that you could take mechanical energy of movement and turn it into heat. Okay? Something obviously we know very easily. That happens all the time. Okay? So scientists started to realize that heat and mechanical energy were different types of energy, and they could be converted from one to the other. Not necessarily very efficiently, but it could happen. Okay? And that could happen if an object had either kinetic energy, that was the easiest, energy of motion, or potential energy. Okay? But potential energy couldn't be converted into heat directly. It first had to be converted into kinetic, and then it could do work. Potential energy can't do work. Okay? It has the potential to do work, hence its name. Okay? But it has to be converted into kinetic first. All right, and that led to this. the definition of energy, which is the capacity or ability to do work. Okay, said that right off the bat today. Okay. Now we've almost come full circle. Okay, has anybody ever started a fire with the bow and the stick? Okay, like we call it rubbing two sticks together, but it's not really rubbing two sticks together. Okay, where you take, the spindle and the bow, right? So you take like a stick and you got a string on it, you wrap the string around the stick, and then when you move the string back and forth, it spins the stick really quick. Okay, so why does that work? Friction, mechanical energy turning into heat. Okay, if you ever got lots of time on your hands, you can try it even just with your hands. Put the stick in your hands and just keep going, keep going. It's got to be really dry wood though. Okay, don't try and do it with like wet wood. Okay, you'll never get anything started. All right, but if you have really dry material around the point, okay, you can usually get it to start. But it's hard work. Okay. And lots of wear gloves. Yeah. Or have whittled the stick down so there's no bark and splinters or anything on it. Okay. All right, that's why they usually did it with a bow and a rock. What's that? Yes, at that point you want rough, but it's going to smooth itself as you do it. Yeah. Okay. All right, and then Joule. Okay, Joule's probably the most important person here. After all, the units for energy are named after him. Okay. Joule showed quantitatively with numbers, okay, that energy could do work. Okay, came up with two fairly simple experiments that showed the connection between mechanical energy and thermal energy, okay, and that one or the other could do work. Okay. So here are Joule's experiments. Okay, his first experiment was the falling block experiment. Right? In that experiment, he was trying to show, actually in both of these experiments, he was trying to show that potential energy, gravitational potential energy, okay, could be used eventually to do work. So what he did is he had a stationary block, okay, that couldn't move, and he had a thermometer in it. And then he had a falling block, one that he could pivot up and away. Okay? When he pivots it up and away, what has he done? Okay, he's given it potential energy. If he gives it potential energy, what has he done? Four-letter word starts with W. Work. Okay, this goes back to that definition of work. Okay, work is a transfer of energy. Joule transferred energy to the block when he lifted it up. He did work. Okay, now when he lets it go, that potential energy turns into kinetic. It falls. Okay, that's just the natural way of things. When it's smashed into the stationary block, what happened to the temperature of the block? Went up. Okay, he showed quantitatively here. This is one form of energy being turned into another. The only way that block could get hotter was from that collision. Nothing else happened to it. Okay? Same thing happens if you take a hammer and you're pounding like a nail into wood. You just pound the wood. Put your thumb where you were pounding, it'll be hot. Okay? It's turning mechanical energy into heat. Okay? All right, he showed it another way with a bit more complex experiment. Okay, he put falling masses on pulleys. Okay, he had these fan blades inside a jar of air. Okay, and when the masses would fall, okay, the blades would spin. There'd be drag, air resistance within the jar, and the temperature inside the jar would go up. Okay, kind of a more complex way of showing exactly the same thing. Okay, but a little easier to show the amounts of energy because he knew the masses of everything. Okay, a little easier to show. Okay. Making sense? All right, we're going to leave it there today because that kind of brings us full circle. Pardon me? Of the experiments? This one was just the falling block. This one was the falling masses.